Welcome back to Topics in Statics. We're about to try and think a little bit about equilibrium in two dimensions. Now my condition for equilibrium in two dimensions, I've got three conditions. The first is that the sum of the forces x is 0, sum of the forces y is 0, and then the moment about some point O also has to be 0. And that seems fairly standard. That's the way we've done problems in physics. That's the way everybody tends to think about this. But there are some other options. For example, I could also use one force equation and two moment equations. Now, if I do this, there's some restrictions on what those moment equations have, what has to happen. Right, I calculate the moment about A and the moment about B. The trick is that, right, in this case, I've eliminated the y equation, the forces in the y direction. So points A and B, if I draw a line through the points A and B, it can't be parallel to the y-axis, the one I eliminated. So the way I typically use this is I have a beam problem. Here's A, here's B. Then I would use some of the forces X, some of the moments about A, some of the moments about B. It depends on the problem, but that would be perfectly okay. If that beam was tilted on its side, I couldn't do this. I couldn't use some of the forces X and moments A and B. Similarly, another alternative is I can do three moment equations. I can just use some of the moments about A, B, and C. Now here the trick is A, B, and C cannot lie along the same line. So I'd have to pick 3 points A, B, and C. And those 3 points have to define a plane, in which case I could do this moment equation. It's just a possibility. That doesn't mean I necessarily am going to ever do it, but it's a possibility. Keep it in mind. Right, under certain conditions, I don't need all three of those equations. Right, the most important cases to consider, if all the forces are collinear, all I need is one equation. The sum of the forces X has to be equal to 0. That's all that's required for the object to be in equilibrium, if all the forces are collinear. If the forces are in a plane and all the forces are concurrent at a point, then I don't need a moment equation, because about that point, there is no moment. Those forces don't produce a moment about that point. And then the third case, if I have parallel forces all in a plane, then all I need is the sum of the forces in that one direction, whatever direction the forces are, and then a moment about some point in the plane. An important thing that comes up a lot is when you have 2 or 3 force members. These are typically, we'll do more of this when we get into structures, but if I can recognize that an individual member of a structure is subject to either only two forces or only 3 forces, particularly the 2 force. The 2 force member has a force applied at only 2 points on the member. So if that thing's going to be in equilibrium, the only way it can be in equilibrium is if those 2 forces are same magnitude, opposite directions, and have the same line of action. So no matter what the shape of the object is, for example, you may have a piece shaped in a bow. If it only has 2 forces acting on it, one at this point and one at this point, those 2 forces have to be equal and opposite. They have to be. And so I know what the line of action has to be between those 2 points. It has to be. Those 2 forces could point, right? I've got them pointing towards each other. They could point away from each other equally, but they've got to lie along that line. three force members, if I've got three forces and that's all acting on a beam or on some, then those three forces have to be concurrent. Sorry. In one case, if I have three forces that are concurrent at a point, then I can just sum all those forces to zero. Add them up. I can draw a triangle and sum all those forces to zero. Right? If those three forces are the only ones acting on this beam, I can draw a picture that says, here's F1, here's F2. Sorry, F2 needs to go further than that. Let's try this again. Here's F1, here's F2, here's F3. That has to be true because those are concurrent at a point and they have to add up to zero, and the only way they can add up to zero is if they make a triangle like that. If the three forces are a parallel force system, right, they all have to add up to zero, and then I need a moment equation to get the moments to be zero. And that's all I need. Next time we'll talk about systems in 3 dimensions.